Well, hey there, Calcsters. I'm a little late on my weekend review and preview, so thank you for tuning in. I wanted to talk through the things we've been focusing on the last week or two, which is the power rule, the equation of a tangent line, and displacement, velocity, and acceleration, and then introduce composite functions and the chain rule. So if you remember, the power rule works when we have power functions. So that's x or some expression containing x raised to a power. And when we have that, we can find the derivative by bringing the power down, multiplying it by any coefficient that is currently there, and subtracting 1 from the power. Now, we started with some pretty basic examples, such as x cubed plus x squared minus 5x plus 10. Now, when we have multiple terms, it's just like we have little mini problems within one problem. We use the power rule for each one. So the derivative of x cubed would be 3x squared, because I brought that power down and subtracted 1 from the power. The derivative of x squared would be 2x. Brought the power down, went to 1 less power. The derivative of minus 5x would be a minus 5. And the derivative of a constant is 0, because the slope of a constant function is 0. Now, that was one of our straightforward examples. We also looked at problems that contain fractions, which becomes more complicated simply because of the algebraic complexity that comes with that. So let's say we had 2/3 x to the 1/7 minus 3/4 x to the negative 1/5. Or let's do negative 2/5. Now, when I take the derivative, the process is exactly the same, right? So I bring the power down. I go to 1 less power, which you'll remember my trick is always to subtract 1 with a common denominator. So instead of subtracting 1, I subtract 7/7 if I have a denominator of 7. And for the second one, I'm going to bring the power down and go to 1 less power. Now again, on these ones, the process is the same, but the algebra you need to be careful with. When we multiply fractions, we multiply numerator to numerator and denominator to denominator. And here, we're going to be subtracting a negative, which I will change to plus a positive. That'll be 6/20, which I can simplify. Now, subtracting a negative means I'm going to have a larger negative number, so negative 7/5 is my exponent. And 6/20 I could simplify to 3/10. Right. And that's our power rule. Now, with the equation of a tangent line, you'll remember that there's a few things that we pulled from our past, all right, like this point-slope form of an equation. And we're using the fact that what we've talked about since, first, second week of school is that the derivative is the slope of the tangent line. Okay, so here is the tangent line, here is the slope. The derivative is the slope of the tangent line. So let's say they want us to find the equation of the tangent line for y equals 5x squared minus 7x when x is equal to negative 1. All right. Now, I need an x value, which I have right here. I need a y value, which I can find using the original function. And I need the slope, which is the derivative evaluated at this x value. So first, let's find that y value. I'm going to plug negative 1 in for x in the original equation. Negative 1 squared is positive 1. It'll end up being plus 7, so that'll give me 12. So I know when x is negative 1, the y value is 12. Now, the other thing I need to know is the slope, and the slope comes from the derivative. So I use the power rule, and then I'm going to evaluate the derivative at negative 1. So 10 times negative 1 minus 7, negative 10 minus 7, which is negative 17. So now I have everything I need. I've got my slope, which is negative 17. I've got my y value, which is 12, and my x value, which is negative 1. So to write my equation, I would do y minus the y value, which is 12, equals the slope, negative 17, times the quantity x minus negative 1, which of course I could change to x plus. I'll have to rewrite that. I could rewrite as y minus 12 equals negative 17 times x plus positive 1. Now, lastly, on our review piece, we looked at displacement, velocity, and acceleration, right? And most importantly, we looked at, to find rates, we need to take the derivative. So in many situations, we started with a height equation, something that often involves negative 16t squared, and that's related to the acceleration due to gravity in feet per second squared. So let's say we have negative 16t squared plus 8t, and we'll just leave it at that. All right, and let's say we want to find the velocity equation. Well, we do that by taking the derivative of the height equation. So if I take the derivative using the power rule, I would get negative 32t plus 8. So this would be my velocity equation. My acceleration equation is the second derivative of the original, or the derivative of velocity. So in this case, that would simply be negative 32. And again, that's because in many situations, our acceleration is due to gravity, and this is gravity in feet per second squared. Now, oftentimes you're going to be asked questions about what's happening with the object at certain times. So the question might ask, at what time does the object reach its maximum? So what we're using as the information we need to solve this problem is the fact that when something gets to a maximum, it's changing directions from going up to coming down. And for a split second, the velocity is 0. So the velocity is 0, which means if I take the velocity equation, I can set it equal to 0 to figure out what time that happens at, which is what I'm looking for. So in this case, I'd subtract 8 from both sides. I'd get negative 32t equals negative 8. Dividing both sides by negative 32, I'd get t is equal to 0.25, or 1/4. So that means 1/4 of a second into its flight, it reaches its maximum. Now, if I wanted to know the height of the maximum, I can evaluate the original function at 1/4. So negative 16 times 1/4 squared plus 8 times 1/4. That would give me negative 1 plus 2, which is 1 foot. This thing doesn't get very high up in the air. All right, so that's a little review on displacement, velocity, and acceleration. Now, here is the preview. So what we want to preview is both the idea, something you've seen before, of composite functions, as well as the chain rule, which is our way of taking the derivative of composite functions. Now, a composite function is a function that has multiple levels. Okay, so it's not as simple as just your basic polynomial or linear function, whatever it is. So an example might be something like 3 times the quantity x squared minus 5 raised to the 4th power. All right, so what you're going to notice is there are multiple things going on here, but in everything we have kind of like our base function and then what's happening on the outside. So in this example, this would be a 2-level composite function. The inside level would be x squared minus 5. The outside would be 3 times the quantity to the 4th power. Okay, so like those two pieces. Let's look at one more example. Let's say we have y equals 5 sine of 3x squared. So this would be a 3-level composite function. The outside or working from the inside. Let's go inside out. The inside would be 3x. The middle would be the sine function. And the outside would be 5 times the quantity in brackets to the second power. All right, so this first idea, composite functions, is just identifying the different levels that exist within a function. The whole purpose of us doing this is so we can utilize a chain rule. And the chain rule says if y equals g of f of x, so a composite function, then y prime is equal to g prime of f of x times f prime of x. So it's saying we take the derivative of the outside, leaving the inside untouched, and then we multiply by the derivative of the inside. So let's look at 2 examples, right? Starting with number 1 here. If I were going to use the chain rule, the derivative of the inside would be 2x. So the derivative of x squared is 2x. The derivative of minus 5 is 0. The derivative of the outside would be 12 times the quantity to the third power. Okay, so I bring the power down, I go to 1 less power, and then here's the cool part. Whatever starts in parentheses stays in parentheses. We just leave it out, so it's one less thing for our brain to think about. Now our final answer comes from multiplying these 2 together. So I'm going to multiply 2x and 12 for that leading coefficient, which is 24x, times x squared minus 5 to the third power. Okay, not too bad, right? Now, obviously, it's going to get more complex when we have more levels. So here on this second example, all right, I'm going to take the derivative of each level separately. The derivative of 3x is 3. Now, we haven't talked about this yet. Maybe you've predicted it based on some of the problems we've done. The derivative of sine is cosine. And the derivative of 5 times something to the second power would be 10 times that same thing to the first power. Now again, here's the cool part. Okay, whatever starts in parentheses stays in parentheses. So 3x goes in here. Whatever starts in brackets stays in brackets. So sine of 3x. So our final answer in this one, y prime, I'd multiply 3 times 10 for that leading coefficient, which is 30. And then I'd multiply by these 2 in either order. So cosine of 3x, sine of 3x. And that would be my final answer. Now, if that's a little hazy, that's okay. This is just your preview. We're going to do this a lot this week coming up. Thank you for listening, and we'll see you next week.